Homework 5, page 105, section 2.5, and that's the end of chapter 2. 13, 17, 19, 21, 27, 35, 37, 41, 45, 47, 51, 53, 59, 61. That should be 15 problems. And like I said, you're probably going to have longer homework sets this year than you did last year. And that's a good thing. So, let's do it this way. So, what did you guys get? What is the limit? So here's A. The limit as x goes to A of our function f is equal to? 2. What is f of A?
Doesn't exist.
Yeah, and it's better to say it doesn't exist, but it's better to say undefined. Undefined, right? Because there's no specification there. If I plug in an A, it says, well, we don't have any info there. So you could say, and we're going to, if we pretended that this went on forever in that direction and that goes on forever in that direction, we could say that the domain of f would be everything from negative infinity up to A, but not including A. Union that with A up to infinity. Now that's not part of this. It's just, I'm just saying, like, so because it's undefined, and so A is not in the domain of that function, and that's why f of A is not defined. And that's how we draw that, right? So, okay, or we could say there's a hole in the graph or whatever. Okay. Anyway, what about the second one? What's the limit as x goes to A?
Also 2.
Also 2, and it does that, right? Because it's coming from both sides. It's going towards 2. But f, when you plug in an A, you get
3.
3. Okay. What about this guy? The limit as it goes to A. Does not exist, right? Because you're going to two different places. You're going to 3 in this direction, 2 in this direction, doesn't exist. But what is f of A?
3.
Okay, so that does exist. It is defined there. It just happens to be that that's not doing it. Okay, what's the limit as x goes to A?
Blows up.
Yeah, well, it doesn't exist, but
It
blows up, yeah.
Good. So we could write infinity. We could write does not exist. But when you write infinity, it does mean that it does not exist. There is no limit. It's unlimited, right? It goes up forever and ever, okay? But what is f of A?
2.
It's,
Wait.
yeah, you see, I know, and you've probably never seen that before. We've never, in fact, I'm sure we've never seen that before. And, yeah, so in that case, it's 2. And if I didn't put anything there, right, if there was not a dot there, we could say f of A is also undefined, right? The same way that this is undefined. Only in this case, that usually occurs from something like this, and x minus A looks like squared because it's going up on both sides. And indeed, division by 0 is undefined. So it's kind of nice, like you have that similar terminology in both cases. You just say it's not defined. In this case, it happens to be defined. It's 2. Whatever. And one thing I want to say that what we're about to talk about, it'll be the same whether or if something blows up somewhere, like whether it's defined or not, like it happens to be defined there, it could be undefined there. The thing that we're about to say will hold in both cases. I just didn't want to have to draw another graph up there. Okay? Now finally, limit as, now you may not be able to see very well, but what do you think that limit is? It looks, otherwise I wouldn't have written the 2. Right, okay, yeah. And so then f of A is,
2.
one of these things is not like the other. Can you tell which one is not like the
which
rest?
one is
They're all kind of different.
the fourth one? Because it's
Okay, yes, and
Right.
indeed, that one is unlike the other ones. There's something else, though.
The fifth one is continuous.
the first one is the only uncontinuous one.
Yeah, and you see, you even use the word. This one is continuous. Today we're going to be talking about continuity. That's the big topic. It's a huge topic in mathematics, and we're going to blow right through it because and it is central to calculus. Like what we're going to be doing will be on continuous functions. When we're doing calculus, you better have a continuous function. But these exercises right here will be enough to get us to where we need to be. And we could spend 2 days talking about this. I'm not going to. Because you'll see, it's very intuitive. You even said it. You're like, that's continuous. And we haven't even defined continuous yet. But yes, indeed, this is continuous. And let me give you a definition. Let's do black here.
the domain is all real numbers? Or
What now?
if the domain is all real numbers?
Nope, it doesn't have anything to do with that, actually.
Oh.
So here's the definition. A function is continuous at a number, call it A, if the limit as x goes to A of that function is equal to what you get when you plug it in. That's what continuous means. That is the definition of
Oh,
continuous.
so some of the other ones aren't continuous either.
None of the others are continuous. Why? Because, well, if the limit doesn't exist, it obviously can't equal something. Right? Yeah, like, these don't agree, right? You plug in f of a, you get out a 3, but the limit is 2. Okay, so that's not continuous, just by definition. And I'm going to give you a more intuitive definition in just a second. But here, it's undefined there. It's not continuous. And if you're just using continuous in like just regular vernacular, right? You'd say, if I were to ask you, is that continuous? You'd be like, well, there's a hole there. No, it's not continuous. And that is kind of what we mean here. Okay, here there's a jump. We're going to get into these different kinds. Each one of these has a discontinuity at A. Okay, there are different types of discontinuities. This one is continuous. And geometrically, what a continuous function is, and here's the intuitive definition. A function's continuous if you could draw the graph of the function without taking your pen off the board, right? You can't do that here, there's a jump. You can't do that here, there's a jump. You can't do that here, there's a jump. You can't do that here, well, you can't ever really get to infinity. But you see the idea, right? Like, in order to draw this, I have to take my pen off and put it back down. But the rigorous definition here is this right here. Actually, the rigorous definition is you would translate this into the rigorous definition with an epsilon and a delta, blah, 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 blah. But that's the idea, right? And so this is as rigorous as we need. It's quite rigorous. You just replace the thing with the epsilon and the delta, and you got that. Okay, so now here we go. Here are the different kinds of discontinuities. These two are called removable. These are removable discontinuities. Why? Well, because you could get rid of the discontinuity by redefining it at one point. If I said, here's f, but we'll redefine, like for this one right here, we could say, let's define a new function, g. And it's equal to f, that original function, whenever x is not equal to a. But it's equal to what when it is equal to a?
2.
It would have to be it's equal to 2 when x is equal to a. You've redefined one point, and that's what it means. It's you could remove the discontinuity by redefining it at one point. This type of thing, you can imagine, we've seen this before. This type of thing could be something like this. An x squared plus 2x plus 3, x minus a over x minus a. That might be that function right there. Why is there a hole in the graph? Well, because you can't plug in an a. But we could redefine it by getting rid of that one point, which technically would be like this. And you say, well, since that's f, we could redefine it to give me a new one, which would just be x squared plus 2x plus 3. And we could thereby remove the discontinuity. I was about to say remove the singularity. There's a thing in complex analysis. We talk about complex numbers. They're removable singularities, which is very similar to this, and it's kind of like this. When you divide by 0, it's called a singularity. Okay, so this one's called a jump discontinuity. Can you tell why?
Because there's a jump.
There's a jump, right? The graph jumps. That's nice. Like, obviously that. You can't remove that, because you'd have to redefine all of it, really, infinitely many points, because we're assuming here that we're not just doing A, B, C, that when you draw something like that, it's continuous. It goes through all the real numbers.
When f of x is bigger than a, that's like f of x minus 1 or something.
Yeah, right, yeah, but that would be redefining it at infinitely many points. Yeah, and that would do it. Okay, this one right here is called an infinite discontinuity. Okay, obvious. Why, right? And that's true whether or not it's defined there or not. It's still discontinuous. And it's called an infinite discontinuity. Anytime there's an asymptote. And it doesn't need to be going that way. It could be going two different ways, like tangent does. Yeah. That's in all of those cases where there's an asymptote, it's called an infinite discontinuity. This one, though, is continuous. Why? Because the limit as you go there, and we're going to say it's continuous at A, right? At that number. It's continuous at A because the limit as you go to A is 2. And when you plug in an A, you get out at 2. Remember when I said, all of those limit laws that we did basically tell you, just plug it in?
Yeah.
Continuous functions are the ones where you could just plug it in. And wherever that function happens to be continuous, that's where you could plug it in. Now, we haven't talked about something being continuous in many places. Right now, we've only said add a given number. Okay? Yeah, let's do this. Okay, now, this one is continuous from the right at A because what is that? Equal? Right, because as we're going from here, it gives you 3. And if you plug in an A, you get a 3. So it's continuous from the right. I'm not going to write that up there. I could write definition. A function is continuous from the right if the limit as x goes to A from the blah, right? And so there's continuous from the left, continuous from the right. Again, it's not a big deal, and it's pretty obvious, okay? But just so you know that if it's defined there, now it's not continuous from the left, because when you come from here, when you come from the left, the limit would be 2, but when you plug in an A, it gives you a 3, so it's not continuous from the left, it is continuous from the right. Am I blowing anybody's mind yet? Anybody confused about any of this?
I don't think so.
Okay, yeah, and again, this is one of the reasons we're not going to spend a lot of time on this is because you probably already had a feeling for this stuff anyway. And that feeling will get you far in what we're doing. So here we go. New definition. A function, f, is continuous on an interval. So continuous, and now we have continuous on an interval if it's continuous at every point on the interval. Okay. So continuous function, and when we say a continuous function, we're talking about it being continuous on an interval. That's the only way you could have a limit, really. You can't just have a limit at one point. You know what I'm saying? Even this kind of stuff right here, you had to have some kind of interval on which f was defined in the first place, right?
Yeah.
And so we're going to call functions. We're going to say continuous functions. And like this one, for instance, the way I've drawn it looks continuous whenever x is bigger than a. And we could say, okay, where f is continuous, and that we're talking about the interval. Here it looks like this function is continuous everywhere. The interval would be like all real numbers, so on and so forth. The more I talk about it, the more you'll get a feel for it. And again, we could spend a lot of time really drilling this stuff into our heads, but as we just start to do it, you'll get a feel for it. I think it's better to just kind of blow through this, etc. Okay. You guys got all this? Can I get rid of all this stuff on the board?
Yeah.
Okay, I'm getting rid of the homework. You guys got the homework?
Yeah. Yes.
Okay. All right. Okay, so number 16. Explain why the function is discontinuous. I'm going to use CTS for continuous from now on in this class. CTS is continuous. Okay. Continuous at a equals 1 and graph. We're going to graph this one. The next one we won't graph. We'll see why. So here we go. F 1 over x minus 1 if x is not equal to 1, and 2 if x is equal to 1. And here we're evaluating it where a equals 1. So how could we show that something is discontinuous? Think about the definition of continuous. What are we going to need to do?
Take the limit.
Take the limit at the point that we care about. Okay, because that's what the definition means. So sometimes you can really get caught in the weeds here. Don't do that. Like if you're ever like, wait a minute, how am I going to show something? 9 times out of 10, if you just go to the definition, like that will tell you what to do. So 1 over x minus 1 is the same thing as 1 over x, but now it's been shifted right, so it has an asymptote here at 1. And now we could see, okay, this thing does this. It does this, there's 1. Okay, so what is the limit as x goes to 1 of f of x?
It
Doesn't exist. And so we could just say, well, the limit doesn't exist, so it's not continuous. You could be more specific. You could say it has an infinite discontinuity because the limit doesn't exist, or something like that. Who cares? I didn't finish this function. It's actually this guy right here, because when you plug in, right, you plug this guy in at 1, you get out a 2.
That doesn't really matter.
And it doesn't matter, because once that doesn't exist, you can't be continuous because it doesn't exist. And so you could be done, but you could be more specific about it, but yeah. Okay. Same question, or same kind of question here. And it's number 20. Yep. Explain why the function is discontinuous at a equals 3, and we're not going to graph because now the last one helped. The reason I graphed the last one was because I just wanted, like, it helped me, right? It's easy to see once you graph it. This one just looks harder to graph, so I'm not going to bother. But there will be some work to do. Here we go. Okay, so 2x squared minus 5x minus 3 over x minus 3.
Yeah.
Can you see why it's discontinuous there? Yeah. And 6 at x, oh, I'm sorry. So this is when it's not equal to 3, and this is when it is equal to 3. Okay, why is it discontinuous?
You can't plug in a 30.
Yeah, so we could say this. We could say it's discontinuous because this is not defined.
Yeah. So as long as you can prove one case.
Yeah, and like...
Well, f of 3 is defined.
Oh, yeah. I'm sorry. Thank you. f of 3 is defined, but
There's a hole.
there's a hole in the graph, right? And ooh, so is it? And so this is why we're doing this one, because you think, because what if?
Yeah.
What if? And here's the thing. Like, I'm going to take this 2x squared minus 5x minus 3 over x minus 3. And what we need to consider is the limit as x goes to 3. right now you could see, okay, but remember with the limit, yes, there's a hole there, but that might not be a problem, because remember, if you could factor this thing out and cancel these, that just means that there's a hole in the graph. If this cancels, our best bet is that it breaks up something like this. So that first one's going to have to be what?
2x. And the other one's just plus
one.
1.
Because
Because
A plus 1. It's going to have to be. And oh, lo and behold. So this limit does exist. What is this limit?
plug in this 3.
Plug in a 3.
7. Yeah, 7. Oh,
But
but
that's a
okay.
different function.
Ah, and so if this were a 7, then it wouldn't be discontinuous, would it?
Yeah. But it's
That would be how you would fix this function. If you just had that function, be like, it has a discontinuity at x minus 3. I mean, I'm sorry, when x equals 3. Then you could say, well, if we define this to be 7, it's no longer discontinuous, because that would be a removable discontinuity. But here, so the reason why is because the limit as x goes to 3 of f of x is not equal to f of 3, because f of 3 is equal to 6, but the limit is equal to 7. That's why. So you can't just stop. Well, with ones like this, right? The other one, there's no way around it. In this case, we had to check and see, does that limit exist? Does that make sense?
Yeah.
Everybody got that? And so you think, well, it's not defined there. Yeah, it's not defined at 3. That part isn't, but this part is. Yeah, so then you have to check. Okay. And so this is a removable discontinuity. You could just redefine that thing as 7. You just say g of x equals this there, but 7 when this is there. And you're good to go. Now you have a continuous function. Okay. Oh boy, here we go. Here's a couple of theorems. Here's like 5 theorems. Okay, here we go. The first one, theorem. If f and g are continuous at a, and c is a constant. Everybody got my abbreviations?
Yes.
Then the following are continuous at a. Okay, so f and g are continuous at a, then so is f plus g. So is f minus g. So is some constant times f. So is f times g. And finally, f over g is also continuous just as long as
G is not 0.
g of a is not equal to 0. Right? Because we're talking about being
Oh, yeah.
continuous at that. Because we don't know what f and g are doing somewhere else, right? F might look like this. Here's a. It does something like this, but then it does this. And then it does this right here. Right? This might be f. It's continuous here. We don't really care about the other places, okay? But right here it's continuous, and that's what we care about right now. So we're not going to call the function itself continuous, but it's continuous at a. So does that make sense?
Yes.
Okay. So if f and g are both continuous at a, then so are all these things. We're not going to prove these. You know why? Because they come from the limit laws. Think about it. To prove that something's continuous,
Oh.
right, you just do that. It's if this thing is equal to that thing. And so now, well, is f plus g continuous at a?
Yeah.
G of x, is that continuous? Well, the limit law tells you that this is the same as this.
Okay.
And since they're both continuous, then this is the same as f of a plus g of a. Oh! Yeah, and so they all just follow straight from the limit laws. We don't really need to go through that. And it's kind of interesting, right? We spent all year thus far, we've just been working with limits. And now, like, what am I saying? all of that really has led us to this. Like, all of that buildup was really to get to here. Like, that now, because you could do calculus on continuous functions. We'll see what we're talking about soon. But all of that buildup, now that you've spent days and days doing limits, this should all feel very familiar, because you're like, well, yeah, now I know what a limit is, and if you're going to A, it's going from both sides, yeah, and now you're just saying that you'll actually get there in the middle, right? Like, that's the only new thing. In other words, like, and I think I said this a minute ago, continuous functions are the ones where, in the limit, you could just plug it in. Those are exactly the ones that work. Like, that is the definition of it, right? We said a function is continuous at A if you could just plug A in and that's what you get. You get the same thing as when you take the limit. So these should come as no surprise, right? If both of those have this property, if F and G both have this property at some number A, well, then the limit laws tells you, then you just plug it in, right? Your only problem is if, like, it may be continuous there, but if it's 0, well, now, obviously, you have something's going to blow up, and that ain't continuous, right? Here's another theorem. Two parts to it. All polynomials are continuous everywhere. That is, on all real numbers, which is the interval, negative infinity to infinity. So whenever we say everywhere, we mean all real numbers. We're going to prove that one. 2, all rational functions. Now remember, rational functions is one polynomial over another polynomial, right? That's how we define rational functions. So one polynomial divided by another polynomial. All rational functions are continuous wherever they're defined. So there's an example. X squared plus x plus 1 divided by x minus 7 is continuous everywhere except for where?
7.
7. That's the only problem, right? That's the nice thing here, right? Is that a continuous function? We haven't proven it, but that part 1 says, yeah, it's a polynomial. Is that a continuous function? Yep. Okay. It's a polynomial. Yeah, that's continuous. And so, is it continuous? Well, there's your problem right there. Wherever it's not defined, everywhere else is fine. You only have that one problem right there. Everybody got that?
Yeah.
Makes sense. Like, and that's another thing. And that's about this, and why we're going to blow through this so quick is like, this should just be, it should be obvious, really, you know. So, okay, we're going to prove part 1. All polynomials are continuous everywhere. Proof. Give me any polynomial. Okay? Any polynomial, every polynomial can be written like this. Some constant times x to the n. Plus some blah, 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 all the way down to some other constant, x to the 1, plus some other constant. Right?
Yes.
Every single polynomial can be written like that, right? So you give me any polynomial in the world, it looks like that.
Yes.
Okay, so now I claim that it's continuous everywhere. So let A be any real number. Let A be any real number. And let's just check out what is the limit as x goes to A of this function. Well, that's the limit as x goes to A of all this stuff. C in x to the n, all the way down to C1x plus C0. Now we just use limit laws and say, okay, limit of a sum is the sum of the limits. So we have the limit as x goes to A of C in x and n plus, and so on, all the way down to the limit as x goes to A of C1x plus limit as x goes to a of c0. Now we use limit laws again. The nice thing about this, what's the limit of a constant?
Just the constant.
Just the constant. Constants come out, right? That was part of the limit laws. How nice. And so I'm going to pull constants out. Cn times the limit as x goes to a of x to the n. And we use the limit laws again and say, well, that one is just, what is that? What's the limit as x goes to a of x?
A.
Okay, c0. So this is just, that's just a times c1, so that's c1 times a, yeah? Okay. All the others are the same. Now,
N goes outside the N.
yeah, okay, yeah, I like that. We can do this. We could say, well, that's the same as this.
And the
X
limit
goes
of
to
x
a of x. That's just a, so that's Cn a to the n plus all these down to C1a plus C0. Okay, so that's one half of the definition of continuous. What's the other half of the definition of continuous? It has to be equal, this has to be equal to?
P of A.
Yeah, and so we're asking ourselves, is this the same thing as P of A? Well, if I plugged in an A, this would be Cn a to the n plus all the way down to C1a plus C0. So yes, indeed, the limit is equal to the thing, and so therefore, all polynomials are continuous everywhere, because I said A could be any real number. Rational functions are the same. Why? Because of this. The only place they're not defined is when the denominator is equal to 0.
Yeah.
Same proof, really. Right? So, everybody buy it?
Yeah.
Polynomials are continuous everywhere. Everywhere. Rational functions are continuous everywhere that they're defined. Wherever you don't divide by 0, they're continuous. Okay? Another theorem. These are continuous everywhere in their domains. Polynomials. Yeah, I know, we just did that. Why did the book say that again? Okay, let's write it down. Rational functions. I just said that. Why did they say it again? I don't know. Just to have it all in one nifty little theorem, I guess. Also, root functions. Right? That also comes from the limit laws that we had. Right? The root, something to the nth root, it's the same as the limit, and so blah, blah, blah. Here's one that the book doesn't even bother to prove. Trig functions. That's really easy to that we'll be able to show that really easily later on in this class.
Wait, but is tangent
In their domains. So, the domain of tangent does not include these guys. And so that's the kicker here. It's like, tangent's obviously not continuous here at pi over 2. But pi over 2 is not in the domain of tangent. So you're kind of, it's kind of a cheat, But this is just nice to remember here, right? Everywhere in their domain.
So basically there's no just like holes that like jump.
Right, there's no jumps, there's no holes. You could draw it without taking your pen off the paper, right? Except for there, but luckily that's not in the domain anyway, so you don't need to worry about it. It's continuous everywhere else.
What about exponential?
Oh yeah, that's like the most continuous function.
Okay.
It's about as continuous as you could get, and we'll see that. We'll see that soon. Okay, one more before we. Oh no, two more before we get an example. All right, here's 2 more theorems. And again, we're not proving this stuff because we're just blowing through because it is, okay. If G is continuous at A, the number A, and F is continuous at G of A, Oh, no. Oh, well, that's the next one. Whatever. At g of a, then the composition f of g, in other words, f of g, that function that you get when you put that one inside that one, is continuous at a. So there you go.
Oh yeah.
You see what I'm saying here? So like if you have something like this, and you have something like this, let's call this your f. Let's call this your g.
So
Okay. So, and let's say that a is 1. So g, well, that's continuous everywhere, right? It's a polynomial, so it's continuous everywhere. And so we just need to ask ourselves, okay, g of 1 is 2. Is that continuous at 2? Yeah, so therefore, f of g of x, which is root x squared plus 1, is also continuous there.
yeah, because it
Okay.
can never be negative.
Yeah, and that's why I chose that, because that's not in the domain. And so root functions, we should say where it's not, where it's negative, but it turns out to be continuous there anyway. Yeah, so, but we're only dealing with real numbers, because when you don't deal with real numbers, you open up the whole Pandora's box of other things that we don't have time for. So, last one. If f is continuous at b, and the limit as x goes to a of some function g of x is equal to b, then the limit as x goes to a of f of g of x, which is why I said I did these backwards. This one should have been first, but whatever. Is equal to f of the limit as x goes to a of g of x, which, that right there, as we said, is equal to b, is just f of b. So again, there can, like, if this one, and so this one is the pointwise. If this is continuous at a point, and this one is continuous at a point, right? Or rather, the limit goes to there. Right, that's all we need for this one, is just as the limit goes to there. G might have a discontinuity there. It might be the case that here at A, there's a discontinuity. But the limit goes to this number, B. Then, when you take the limit, it gives you, that composition gives you what you would get if you plug that in.
Yeah.
But if G is continuous, right? G is continuous, then it's just the composition itself, and you don't need to worry about this. So one's kind of pointwise, and it's kind of annoying. Again, like, I'm blowing through this. We could give a bunch of examples to really get, we're not going to really need this. This is all going to be so familiar and intuitive that we're just going to blow through it. So, questions before we go, before we move on?
So you can't you can only pull out the f of x in this case. It's not like a limit law, like where you can.
What are you talking
Not the
about?
last one.
The last
f
one?
of g of x. Limit of f of g of x equals f of limit.
No, this tells us that that when they are, if f is continuous, then you could reverse the order. That's what this tells
But you
us.
can't always reverse.
Not always. F has to be continuous to be able to reverse the order.
Yeah.
Because that is the key right there. F has to be continuous. And then if you happen to have two continuous functions, then their composition is continuous.
Yeah.
And that kind of makes sense. That's kind of a big deal in other classes too. That the composition of two continuous functions gives you a new continuous function. Everybody good with this stuff?
Yes.
You're outside of this homework, you're never gonna like refer back to this stuff. Like, because we're only gonna work with continuous functions. Like every now and then we won't have one and it'll be obvious like what you do in that case, So again, that's why we're not really going into this. I see our time. Okay, we're good. Okay, here's an example. Where is this function, f of x, which is sine x over root x squared plus 5 minus 3, where is this continuous? Okay, I'm just going to walk you through the reasoning here. Okay, from the one of the theorems we had, it says that if f and g are both continuous, then this is continuous
As long as it's G.
wherever g is not equal to 0. Okay. So if we could find an A where that is equal to 0, then we'll know it's not continuous there. But that's if f and g are continuous. So is the numerator?
Always continuous.
There you go. Sine x is continuous on all real numbers. Okay. So now, that's part of it. So since sine x is continuous on all of those, the only problem we really need to worry about is where is the denominator equal to 0?
So set it equal to 0.
So let's do that. Actually, but here's the reasoning, okay? Now, so remember, it's this starts with if f continuous and g continuous, then this. So now we need to see. So sine's continuous on all real numbers, don't need to worry about it. So now here's the question, is where is this continuous? And again, in the real world, you'll just do what I said. You're just going to say, well, just set the denominator equal to 0, because obviously this is continuous. But we're going through this just in case you have a harder problem. This is the kind of reasoning you're going to need to do. Check that the top's continuous. Okay, it is. What about the bottom? Is that continuous? Well, let's see. The sum of two continuous functions is continuous. Okay, so minus 3 is just a constant function. That's continuous. Continuous on all reals. This root is but that's a composition of stuff, right? So, okay, we could say x squared plus 5 is continuous on all reals. Root x is continuous on 0 to infinity. But I could okay, that's fine because this is that's never 0. It's always bigger than 0.
Yeah.
And so x squared plus the square root of that is continuous where?
On all
reals. All reals, because the input goes into here first. And since the output keeps you in here, you're good to go. Again, you know this stuff, right? This is why we're not spending a ton of time on this. Like, you could do this on your own. And you've been trained for this for a while, right? So, now then, okay, so, therefore, root x squared plus 5 minus 3 is continuous on all reals. So we're back to here. F is continuous on all reals. G is continuous on all reals. The only problem we have to figure out is where is G equal to 0. And that's what we're going to do right here. I think you're right. Where is that equal to 0? Well, that's where this happens. Square both sides and we get this. That's where this. And so that's when x is equal to what?
Plus or minus.
Yeah, both of them. Be careful with that.
Yeah.
Right. So both of them make this blow up. So in interval notation, where is f continuous? F continuous on
negative infinity.
There you go. Negative infinity
Minus 2.
to minus 2.
Union.
Minus 2.
Minus 2 to 2. Soft bracket.
Minus 2 to 2.
Union to infinity.
There you go. You guys know this stuff, right? This is why for 2 years, we've done problems like this because I didn't want to spend a lot of time doing this, right? Like, it's the same problem where I said, what's the domain? What's the domain of this thing? And yeah, it's pretty much the same thing. Now it's just, now we could mix signs in there and other types of stuff, right? It's not just polynomials that we're working on, but the idea is the same. And it's always going to come down to something like this. Like, of course, it's continuous on its, all of these are going to be continuous on their domains. And the only real problem usually comes down to this. You might have one or two where they're trying to be tricky, you know, and they'll give you something that, oh, that's funny. I wrote down the wrong answer. So, yeah, so whatever. Okay, here's a big one. This is such a big theorem. This theorem is so important in so many things. This is called the intermediate value theorem. Value theorem. And we're going to name it IVT. It's so important that we're giving it a name, IVT. Suppose f is continuous on the closed interval A to B. It might be continuous further out, that's fine, but right now we're just concerned with the closed interval A to B. Now, let n be any number between f of A and f of B. Now, let's kind of demystify what's going on here, okay? You have some function, it's continuous on some interval from A to B. Okay? So in other words, since it's continuous there, when you plug in an A, you get out some number, f of A. Well, not since it's continuous, it's a function. And then you plug in a B, you get out f of B. And we're saying let n be any number between the two. So you pick your favorite number between here. There it is, n. Then, oh, and between f and A, f of B, and you just say f of A is not the same thing as f of B. Otherwise, you can't be between them. N can't be between it if they're the same number. Okay, yeah. So, then, and here's the thing, then, there exists a number C in the interval A to B. There exists a number C in the interval such that f of C is equal to n.
Okay, so C can equal A or B.
Yeah, it will be strictly between, and because that's strictly between, it will be strictly between. Why? Well, f is continuous, and look at this. How can you? It doesn't matter how f looks. You could do this, and guess what? It's continuous. You never took your finger off, did you? So it must go through. To get from f of A to f of B, you must go through at least one point. There might be multiple points the way I drew it, but there's at least one that's going to give it to you right there. This is what this tells you, is that there will be a C in the interval where you plug it in and it's going to get there.
So it's basically saying every input in the interval will have an output.
So, another way of saying this is f takes on all values between f of A and f of B. And you could see, like, there's no way that that can't be true. If this thing is continuous, you could try your damnedest to connect these two dots without going through this blue line. Like, try as you may. You're like, well, maybe it goes way up here, and then it comes way down here, and then, back through. Like, you cannot get from there. Like, maybe if I stay really low forever, well, it's a function. It can't just jump. It's continuous there, so it's going to have to, I went through the line. There's no way around it. You have to go through it. That is a property of continuous functions.
Yeah.
Okay, everybody got that? Does this make sense? Intermediate value theorem, very, very useful for the rest of your life. Here's an example why. Number 48. Prove that there is a root. This is the way that they put it. I don't know why they say that. There is a root of the given equation. What's the root of an equation? Given equation? Root means solution to the equation.
Like a square.
Like when x equals 0.
In the given interval. And here's what they give you. Here's the equation. I would say, prove that there's a solution to the given equation in the interval 0 to 1.
So solve for x.
Good luck. Good luck trying to solve for x. And that's the power of this right here. I don't know why they call it, I would say a solution. I don't know why they say root, but that's what they do. I would say, prove that there's a solution to this given equation in this interval. And this is what you do. You say, I have no idea how I'm going to solve that, but I have this. Can we make a continuous function f out of this?
Add x and minus 1.
Yeah, I like that. We could say, you know what? Let's construct a continuous function right here. First off, is this function continuous?
Yes.
Yeah, it's a polynomial plus, which is continuous, plus a root function, which is continuous. And you might want to say that, root function plus polynomial is continuous. Okay? And so, therefore, f is a continuous function. And it's continuous everywhere. So it's certainly continuous here. So it's continuous on all reals, so definitely on 0 to 1. Okay. And so now here's the question, because if you could find that this thing equals 0, then that's your solution to the equation, wherever that is. But how do you do that? Well, this is how we're going to apply this. I'm going to say, wait a second, here's an interval. So let's look at the closed interval, 0 to 1. What happens when I plug in a 0 here? I get 0 plus 0 minus 1 is negative 1. What happens when I plug in a 1 here?
1.
And so, let's just think about what we've done here. You say when you plug in a 0, you get out a negative 1. When we plug in a 1, we get out a positive 1. Since this function is continuous, it takes on all values. It probably doesn't look like that, right? But it takes on all values, in particular, the value 0. And so you could say, okay, since it's continuous, and we know that f of a and f of b, they're not equal, right?
Yeah.
Therefore, there exists a c in the interval 0 to 1, such that, and because 0 is between these guys, right? Like, there any number between, so let's be really, really careful here. We're going to say, okay, since f of 0, there's 0, and f of 1, right? 0 is a number between there, then there exists a c in this interval. Don't know where it is, the theorem doesn't tell us how to find it, but we know that one must exist, such that f of c is equal to 0.
Yeah.
And if f of c is equal to 0, if f of c is equal to 0, then root c plus c minus 1 is equal to 0, which means that root c equals 1 minus c, so c is a solution. We don't know what it is, but we know that it exists. That's very powerful.
Yeah.
Okay. So this is, you're also going to see ones with trig functions, like secant equals 5 sine something. And it's the same kind of trick here. Like, good luck ever trying to find the number. But you could use this and say, well, here's the interval they gave me. Let's check the endpoints of the interval. Oh, hey, one goes here, one goes here, right? That's the idea. Everybody get that?
Yeah.
Very, very, very useful. Well, finally. Oh, we are over time. We'll do this real quick. That was everything we needed to get through, but this is a really cool example. This is number 42. And I'm going to blow through this because we're running out of time. Find values A and B to make f continuous everywhere. Oh, Peter, buddy. Okay, so here's f. X squared minus 4 over x minus 2 when x is less than 2. It's equal to ax squared minus bx plus 3 when x is between 2 and 3. And the book does this. It really should be that. Because you could argue, if it's not that, you could argue, well, it's not everywhere if it's not defined, and I think it was just a typo on the book's behalf. When X, right there. So, really, you have a few problems, right? That's continuous, not continuous when x is 2, but we don't need to worry about that because it's not there, right? And so we don't need to worry about the whole. The problem is going to be matching this guy up to that guy, right? Does everybody see that? Because if I had something like this,
Wait.
on some interval, and then I have this guy right here, right?
That's a line.
Or let's do like how about this? That would be a good one. Find an A to make that true on some interval, and let's say A is...
And so it has to be continued. Okay, yeah.
when x is less than, let's do 2. And here when x is bigger than 2. You say, well, x squared looks like this.
Yeah.
And now you're looking for a line. Well, if it's too far, if it's too low, it ain't gonna match up. If it's too high, we need this to happen here at 2. They need to agree right here at 2 for this to match up.
Okay, so
It looks like just 2 would do it.
yes.
If we had a line 2, it would come through and it would touch right there, and then it would come back up, and that would be a nice continuous function. The idea is linking these guys up so that they touch.
So we need one A that links everything, basically.
Yeah, and that's why this one's tough, because now we have a few things to deal with. First off, let's find the limit as this goes to 2. Okay, so x squared minus 4 over x minus 2, that's the same thing as x plus 2, x minus 2 over x minus 2. So x plus 2, the limit as this thing goes to 2, nope, yeah, as it goes to 2 is what, 4?
Yeah.
So this function's getting closer and closer to the value 4, and there's a hole in there. But now we want this guy to take over. He's got to match up there at 4.
So
And so when I plug in a 2 into this one, I got to get out of 4. Right?
yeah.
That's the idea. A 4 better come out when I plug in a 2 here.
Okay. So we need that.
So 4 has to equal 4a minus 2b plus 3.
But
There's one equation. And actually, let's go ahead.
I see.
Let's go ahead and make that a 1 equals 4a minus 2b. Okay, so there's one equation. Two unknowns. How many equations do we need?
2.
Aha. So we have one equation. 4a minus 2b equals 1.
But now we just do the same thing.
Now we need the same. We need these guys to match up at what number?
3.
So they have to. Those two outputs have to be equal. In other words, we want the output of this to be the same as the output of this
Plug in a 3.
at x equals 3. So we're going to plug in a 3 and we get a 6 minus a plus b has to be 9a
minus 3b.
minus 3b, right, plus 3.
And just combine it.
So now let's get the a's and stuff over here. I'm going to take my 3 over and get a 3 here. Yeah? Right?
Wait,
Oh,
that was
yes.
a B.
Oh, that's a B. The other one. The other 6 looking thing. There you go. Okay. Now A comes over and it gives us a 10A. B comes over
Yeah.
and gives us a minus 4B. Now we have 2 equations, 2 unknowns.
That's it. So we just. Okay.
There's a bunch of different ways
Yeah.
we could do it. Let's make sure, because I put a plus in the wrong place, or I put a minus in front of something last night, got all the way to the end, plugged everything back in. I was like, oh, man, I was really angry. Let me make sure I got these right. 10a minus 4b equals positive 3 this time, yes. And then 4a minus 2b equals 1. Okay, so this should work.
Substitution.
You know, you could. I
Put them
personally,
together.
I liked it. I'm going to say, okay, watch.
I'm
10a, yeah. I mean, you'll see. Because you end up doing the same amount of work.
No
It's
matter
the
what
same
you do.
amount of work. And I'm just so used to this. So I'm going to say, okay, 4 minus 2, 1. 10 minus 4, 3. There's my matrix. I'm going to do this. Now, I'm going to...
It's been a while.
It has been a while.
Yeah,
But
we
I'm going to
need
go
one.
2 minus
won't.
1, 1/2.
Wait, don't we need a 1?
We need a leading one.
You could. And here, you know, I really drilled it into you guys to do it a certain way. I don't really. So I'm going to multiply this guy by -5. That'll give me a
Okay.
-10.
Yeah,
This
that
will
works
give
as
me a
well.
+5. I said -5, so -5/2.
Yeah.
2 minus 1, 1/2. That gives me a 0, a 1. And let's see, 3 is 6/2 minus 5/2 is 1/2. Yeah, positive 1/2. That ain't so bad. Now I'm going to add that to that.
Yeah.
And I get a 2, a 0, and a
1.
1. Oh, 1, 1/2.
Divide by 2.
Now divide the top by 2, and I get 1, oh,
They
1/2.
both
Oh, 1,
equal
1/2. And so that means that A is equal to a 1/2, B is equal to a 1/2. That should be the answer. Let's just check real quick. I was talking to your mom before class, and she was like, it's going to run late today. I was like, yeah, it's going to run late today. Okay, so we need to make sure all of these match up. We know that that works there. We plugged in. Now, we need to make sure that when we know that this goes to 4 as x goes to 2. So this needs to go to 4 as x goes to 2. Now, this should be 1/2. Yeah, I'll put these right down here. This should be 1/2 x squared minus a 1/2 x plus 3. This one should be 2x minus a 1/2 plus a 1/2, which is just 2x.
Yes.
Yeah? Yeah? Minus a 1/2 plus a 1/2. Okay, so they should all agree. I'm going to plug in a 2. 1/2 2 squared minus 1/2 times 2 plus 3. That's the same as 4 over 2 is 2, minus 1 plus 3 is 4. That's what we needed, so that matches up on that side. Now let's match these up on the other side. And so we got, plug in a 3, we have 1/2 times 3 squared, minus 1/2 times 3 plus 3. That's 9 halves minus 3 halves plus 3. That's 6 halves plus 3 is 3 plus 3 is 6. Did I do that right?
Yes.
Okay. Then that guy, when I plug in a 3, needs to give me a 6.
Yes.
And when I plug in a 3, it does give me a 6. And you could, if you wanted to, take this final function that we have, x squared minus 4 over x minus 2, this one, 1/2 x squared minus 1/2 x plus 3, and then finally 2x. And you could graph each one of those functions, like on Desmos, and you'll see that they do link up at 2 and at 3.
Yeah. Okay.
And that's a way you could check your work, right? But I mean, we just check the work and we see. But you understand this kind of question. This thing, depending on what you put in for A and B, they might not match up at these places right here. So we just force them to add up. With 2 unknowns, we need 2 equations to solve. Your homework has 1 unknown, and so you'll need 1 equation to solve. I wanted to do the hard one for you guys and give you guys the easy one because I'm just a nice guy. So, okay, guys, enjoy. I hope this. Oh, and so we're done with chapter 2.
Oh.
That means a quiz is happening soon.
Like when?
I don't know. Either next time or the time thereafter.
Hopefully not next time.
Yeah, we should probably review. We'll review. We'll review next time, then have a quiz.